Okay, in this lecture we're going to start a little bit into Chapter 4. You can see over here that it's entitled Network Access. Since we're going to the beginning of the chapter, I'm just going to navigate through the menus here. And basically, in this chapter, we're going to be talking about dividing the network into layers and talking about the OSI model and TCP/IP model and how we go through and prepare data to be transmitted over the physical network. So we'll be talking about layer 1, the physical layer. We start out most chapters with a class activity. I won't go through, well actually I will assign this one. It should appear in Blackboard and be due in about a week. But it's a 2-page lab talking about communicating and getting information from somebody else, assuming that you were attending a conference. So like I said, expect that to appear in Blackboard. This section talks about connectivity and the different types of connections you might have. Here we have a home router. Kind of looks somewhat like my router as far as the shape, so I assume this might be a Cisco or possibly Linksys, because Cisco bought Linksys router. But on the back, you have a yellow connection, in this case yellow labeled Internet. This would be where you would plug your Ethernet coming from your modem. So that gets the Internet connection to the router. And then you have a place to put 4 physical connections labeled 1, 2, and 3. So these would be Ethernet cables if you needed them. And then you will also have an embedded wireless antenna for connecting all of your wireless devices. So that's what the front looks like. They talk about this as being an integrated service router. I will probably more likely refer to this as a multifunction router because it does many different things. It's a switch. It's a wireless access point. It may be a firewall. It may be a DHCP server. There are many things that this little box does for us in our home, and we'll talk about those throughout the class. And here they're just showing you if you had a laptop that actually had an Ethernet port, which is getting less and less common, you could simply run a cable from the laptop to one of the switch ports labeled 1, 2, 3, 4 on the back. When you have RJ45 jacks where you're going to be plugging in cables like they're showing here in figure 1, you're going to have something called a NIC, which stands for Network Interface Cards. If you have a printer that connects, they have a NIC card. If you have a wireless antenna, it is a NIC card. So everything where it connects to a network, whether it be wired, fiber, or wireless, will all have a NIC card built into them. Here they're showing you a wireless LAN that also has a range extender that will provide, in this case, it looks like there's a bed there and a couch, so it looks like a home, so that you can have wireless inside your home and even outside your home, sometimes for a limited distance, but it looks like they have a patio or a yard where they have a laptop set up. So the physical layer is down at the very bottom of the OSI model, and the physical layer has the responsibility of getting an encoding of data from the source to the destination. and that data that it's moving is just a series of ones and zeros. It'll actually be an Ethernet frame, but it'll be decoded into a string of ones and zeros and sent across the network. The physical layer that would then pass it up to the data link, and de-encapsulation would happen. So I think we talked about this previously, but they have the PDUs here, and the top three layers are data, 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 segment, IP packet, Ethernet frame, and then bits on the physical layer. So they're trying to show that in the middle. You have application data. It gets broken into segments. Each of these segments has an IP header encoded onto it. That IP packet is then packed into an Ethernet frame, which will have source and destination MAC addresses, and then that's converted to ones and zeros and placed on the physical layer. When we get over here, this is just de-encapsulation. We take the ones and zeros, we interpret that as an Ethernet frame. If it's destined for us, we rip that Ethernet frame off. Then we pass it up. We have an IP packet. We look at the IP addresses. If it's destined for us or as a broadcast, we then pull the data out. The transport layer reassembles the data, and then we pass the data up through the session presentation layers to that application layer. So that's just showing you kind of a combination of encapsulation, de-encapsulation, and the PDUs, as well as talking about the signaling on the physical layer. At the physical layer, we have different type of media. The most common is probably copper cable, Ethernet cable. We have electrical signals, different voltages that are used to represent the ones and zeros. If we have fiber optic cable, we have either a laser or an LED pulsing light that is going to be interpreted as the ones and zeros. And then finally, we have different forms of wireless. So at the top here, they're showing a digital signal that may be 1 cent, zeros and voltage is ones. We can use amplitude modulation, frequency modulation, or phase modulation. AM and FM is the same AM and FM that is used in your radios to transmit information. So this is the kind of signal or phase that we would have to represent the ones and zeros in the signal. We'll talk a little bit more about different encodings in this chapter. So TCP/IP is IEEE 802.3. That encompasses the top 5.5 layers, but down at the physical layer you have two different sub layers. It's kind of divided, and IETF controls all these. But when we get down here to the physical thing, the NIC cards, the cabling, etc., you can see there are 5 different agencies that are responsible for the physical layer, and I think we've talked about most of these in the past. Okay, Lab 4124 is identifying cabling and devices. I do assign this when I have students in the classroom, but with this being online course, I didn't really know how to go about this. Basically, I have a bunch of tags like cable 1 through 6 and device 1 through 6, and I walk through the classroom and the machine room that's next to the networking classroom at the Newtown campus, and I just clip this on wires and devices and different things. And the students have to go around and say, oh, cable 1 is a crossover cable, cable 2 is a fiber cable, and that type of thing. So let me look. There's not really a whole lot of description other than what I just said. So if you want, you can read over that, or if not, probably not a big deal. Okay, as far as functions, there are different types of encoding. We like to think of the digital signal as, a lot of times a 0 being a low voltage and a 1 being a high voltage, but in reality, that's not really how it is encoded. So marked off by the little vertical gray bars, we have something called a bit period. And one of the things that happens is, we haven't talked about it yet, but there's something called the preamble that allows the NIC card to kind of figure out where these bit periods are. And once it figures it out, if there's a transition down in the middle of that bit period, it's a 0. If there's a transition up during the bit period, then it is a 1. So you can see that, it goes down, so it's a 0, up, so it's a 1, 0, and then it goes back up and then comes back down, so we have another 0. Then we go up, which is a 1, kind of the same thing. Very quickly we have to come down and then come back up to encode another 1, and then finally the last bit is a transition down. So we have a 0. Let's see if they talk about any of the others. There are other encodings that I often go through and talk about. One is called non-return to 0. That's kind of the easiest way to look at it. We don't have a good graph here, but a non-return to 0, we would have a low voltage, which would probably be 0 volts. We'd have a high voltage, which would normally be 5 volts. And then if we're down at the bottom, we have a 0. If we're at the top, we have a 1. So I will try to show you this on here. Hopefully it's not too confusing. But, well, let's say this is 0 down here, and this is 1 or 5 volts. So if we had a 0, we would stay at 0. If we had a 1, we'd go up here. If we had another 1, we'd stay up here. If we had a 0, we'd go back down. If we had a 1, we would go up and stay there. So either we're at the bottom, which is a 0, or the top, which is a 1. There's also something called 4-bit / 5-bit encoding. What that does is takes groups of 4 bits and encodes them into groups of 5 bits. And the reason it does that is it provides error checking and better performance. And then there's also 8-bit to, or 8B / 10B, which is 8 bits to 10-bit encoding, similar to the 4-bit / 5-bit I just talked about. And then there's one called PAM5, which takes 2 bits at a time and chooses an amplitude based on those 2 bits. So you would have a number of amplitudes, and however high you were up would dictate what 2 bits were being encoded. In the case of FM and AM, we have a modulating wave, and then on top of that we put a carrier signal, and we come out with either a signal whose frequency varies depending upon the data we're trying to send, or the amplitude goes up and down based upon the information we're trying to send. And again, I use this term, but this is referred to as signaling. The signaling is putting 1s and 0s in some representation on some type of media. Bandwidth is a theoretical maximum amount of data that can be sent over the media. And the next section we'll talk about throughput. But bandwidth, if we have a lowercase b, that means bits. And usually the / will be represented as a p for per. So if you had like 100 Mbps, that would be 100 megabits per second. If you had a gigabit, it would be 1 capital G lowercase bps. So they're showing you this. This is how many bits in theory you can do. Now, if you have 100 megabit Ethernet, then the theoretical maximum you could send is 100 megabits per second. But in reality, you might count on getting 80, 85. So you're not going to get the theoretical maximum. Throughput is the actual amount of time that can be moved in a specified period. So I think I've already assigned to you the speed test, but this would look like the speed test. You're getting 80 megabits per second down, about 9 megabits per second up. So that tells you how good or how bad your bandwidth is. If they talk about baud, think maybe they mentioned baud for slower speed things like 56 kilobaud modems. Baud, B-A-U-D, just means bits per second. Most internet connections are asymmetric in nature. I can't remember if I've talked about that before or not, but typically your download speed is much faster than your upload speed. The reason being is you send something up, like a request for a web page. That may just be a few hundred characters. Then you maybe get megabytes of stuff back, images, text, etc. Same thing with email. You say, hey, give me a copy of this email. That email may be 10 megabits. So typically your internet connection is asymmetric, which means the speeds aren't the same. And the download speed is typically the faster of the two, or should be. So here they're showing you different types of connections you might have. Some of these fall in the category of physical media. When they talk about fast Ethernet ports, we're talking about 100 megabits a second. This is a DSL connection. We have management ports, which will be over RJ45, but they'll be serial in nature. This has gigabit, 1 gigabit per second Ethernet interfaces. And then it has type A connectors, which are not for sending network signals, but for plugging flash drives in, or keyboards, or that type of thing that you might need to do. The different things, different types of cables connect to these different ports. They each have a certain amount of bandwidth associated with them. They also dictate what type of cable, like most of these are RJ45s, but these are USB. Those connectors like AJ45 have certain pin ins and pin outs, and they also have a maximum length that they can travel. So when you're learning about physical media, these are some of the things that you need to be aware of. Okay, so this is an activity identifying some things at the physical layer, layer 1. You can do this on your own. Okay, so talking about Ethernet cable that is copper RJ45. So up here at the top left, they call this a pure digital signal. This is the information that we're trying to encode. This is a better example than I did of non-return to zero. That's usually the easiest to think about. Copper cables, if they're in an electrically noisy environment, are able to pick up some interference. So here we have some interference that's being induced on the cable carrying our intended signal. If we add these together, these become our signal. And if we go through and try to read them back and think of them as an approximation of the digital voltage, everything seems fine, except this 0 here. There was enough noise that it became a 1. So because of this interference we had, the signal was not sent intact. EMI, electromagnetic interference, or RFI, radio frequency interference, can cause problems. Also, we have something called crosstalk. Crosstalk is the fact that if we have, for example, in our Ethernet cable, 4 twisted pairs, one signal being sent down, one of those pairs can induce a signal or noise on any of the 3 other pairs. So hopefully that crosstalk is low and we don't have so much crosstalk that we end up with a problem here where our bits are becoming something other than what they were intended to be. This is showing you some different type of cables that might have copper media. Here we have unshielded twisted pair, UTP, which is the most common type of Ethernet cable. Each pair carries a signal. It's twisted to cut down on interference between one pair to another pair. Shielded twisted pair, there's actually a couple of kinds of this. This is the more common. That is, you take what is basically like aluminum foil and wrap it around all the conductors so that if you're in a noisy environment, the signal can't pass through that outer pipe, if you will, to get to the cables that are trying to transfer a signal. You can have some really expensive cable where each of these pairs has their own wrapping around it, and then all 4 of them are wrapped with an outer conductor. That gives you the best shielding, but that's pretty expensive cable. And then down here we have coaxial cable. That means the center conductor and the return, which is also the shielding here, are coaxial. That is, they share an axis. Your satellite TV, your cable TV, things like that use coaxial cable. A long time ago, like in the 80s, maybe early 90s, some Ethernet was run over coaxial cable, but these days we usually use twisted pair for everything. Okay, this is going back and talking a little bit about untwisted shielded pair. I've already told you that the twisted pairs protect ourselves from interference by canceling out noise. They are colored. You'll have a solid wire, like this would be the orange wire, and this will be the orange-white. So it'll be white with orange stripes. This is green and green-white, blue and blue-white, and black and, brown and brown-white. Then you have an outer vinyl or some type of plastic jacket that holds all these wires together and protects it from physical damage. In the case of shielded pair, here this is the more expensive. There are full shields on each pair. You still have 4 twisted pairs. You have the braid or foil, which is protecting all these conductors from electromagnetic or static interference, and then you have a jacket around it again to protect everything. So the addition in this case are the shields that you might have. The outer shield for sure, possibly inner shields on the twisted pairs. In the case of coaxial cable, you have a copper center conductor. You then have an insulator. Copper is a very good conductor of electricity. You want to have something like plastic, which is not a conductor of electricity. And then you have the braid shielding, and then the outer jacket, which is going to protect it. As far as connectors, these are the different types of connectors that you might have. An N-type connector is often to an antenna. An F-type connector is usually what you might use on cable TV and satellite. And then BNC connectors that are quarter turn twist on connectors. These were what was used when I was talking about in the 80s and 90s. That's typically where BNC connectors were used. So these days it's mostly going to be F-type connectors that you have if you're cabling up a network. As far as what they're calling safety, they're considering this more the safety of the equipment and cabling, but you should also make sure that you are safe as an individual or other people around you. Cables need to be plugged in correctly. You should not run data cables with electric power because electric power will introduce noise onto the network media, which may cause problems. You should inspect occasionally things for damage, make sure a door didn't get closed on the cable and nick it or something like that. And then you need to make sure that your equipment is grounded and possibly protected by UPSs. If you're not familiar with the UPS, it stands for uninterruptible power source. And then a UPS also has surge protection, so if lightning hits or a transformer blows up, you try to not have that surge damage your sensitive electronic equipment, in this case, your networking equipment. Okay, this page 4217 is another activity which you can go through and do on your own. Okay, this is going back, talking a little bit more about the cancellation. If you had electricity or electronics in high school, or possibly in an electric class, or possibly in physics, you may have talked about the right-hand rule. The reason twisting the pair cancels each other out is because the right-hand rule, the fields are in opposition to each other and hopefully cancel each other out. The more twist you have per wire, the better it's going to be at that cancellation effect. There are different categories of wires that we will probably talk about, but Cat3 is telephone. The Cat stands for category. Cat5 was Ethernet for a long time, then it was Cat5e, and then Cat6 and Cat7. And as you move up, typically the speed that you can send increases, and at those higher frequencies you need more twist per foot to keep that cancellation effect working correctly. Okay, so here they're talking about, like I said, Cat3 is for landline telephones. Cat5 and Cat5e are for twisted pairs, and then Cat6 is shielded. And one thing, if you click on these plus signs, it'll tell you that Cat5e can be used for 100 megabit per second or gig Ethernet. And when you go up to Cat6, you can technically run it at 10 gigabits per second, but it's not recommended. Typically, when you get up to 10 megabits per second, you're going to switch over to fiber. Here's the different types of connectors that you might have. Most of the time, it's going to be an RJ45 plug, which has 8 connectors and a clip, and you plug it into a jack that looks like this. So this is a jack that fits into your wall. It's going to have color-coded. You bring the wire in, and then you pull the wires like the orange wire, orange and orange-white, brown, brown-white, green, green-white, blue, blue-white, and then you have something called a punch-down tool that drives the wires in these little slits and makes good connection with these metal pins in the middle that are going to press against the pins in the RJ45 connectors. This is a good cable. It has been punched down. The colors are correct, and most importantly, the strain relief has been driven down into the shield to make the connection very, very sturdy. If you yank on this, it's not going to damage it. Here, the wires, doesn't look like all the wires are in the right place, and they made these wires really, really long, so the shield's out here. This is bad because it might be damaged. It's also possibly wired incorrectly. But you have these cables, these pairs, that have been untwisted for a longer distance than we have here, so that's going to also increase the possibility of interference altering our signals. So you want to make sure your cables look nice and neat. There are two standards for the color code and how they match up with the 8 pins in an RJ45 connector. The standard that talks about this is T568. On the left we have a T568A wiring. On the right we have a T568B cable. If you wire both ends to be an A or both ends to be a B, we have what's called a straight through cable. That is, pin 1 goes to pin 1, pin 2 goes to pin 2, etc., all the way up to pin 8 goes to pin 8. If you are connecting like devices, like PC to PC, router to router, you need something called a crossover cable. And the way you get a crossover cable is you put an A on one end of the cable and a B on the other end. And basically that takes pins 1, 2 on the left, maps them to pin 3 and 6 on the right, and pins 1 and 2 on the right get mapped to pins 3 and 6 on the left. So basically what you're doing is you're connecting transmit to receive in both directions. And like I said, that's called a crossover cable. A rollover cable that they say is Cisco proprietary that you use to connect a laptop to a console port. What you do is you either wire one end as an A, and then you take the other end and act like you're going to wire it as an A, but then turn the plug upside down. So that has pin 1 go to 8, 2 to 7, 3 to 6, etc. So it kind of rolls over as you go down the wire from one plug to the other end. So that is a rollover cable. Testing UDP cables. We have tools in the classroom that give us something called a wire map that tells us, you know, pin 1 goes to 1, 2 goes to 2, 3 goes to 5. Oops, you have a bad cable. It will also tell you how long the cable is that's connected to it. And if you have an expensive enough meter, it will tell you about signal loss and about crosstalk that may be present in your environment. Here's a little activity that you can do on your own. Can you drag on figure 1 the colors correctly for a T568A pinout, and on figure 2 it'll be a 568B. So you can do this on your own. This used to be one of the labs that people used to dread. You had something called a skills exam, and that was part of that was making your cables. You had to do it in class. You had to do it with no reference material. Now, I never made my students do that, because the reality is if you're going to make a good cable and you don't want to waste plugs or cable, you're going to look it up. So I would put the figure up on the screen, and you know, the students could make their cable. But since this is an online course, we will not be making cables. So you might want to just read over the lab just to see what you would have done if this was an in-class situation. Okay, switching from copper to fiber optics. Here's a connection or a picture of a 10 gigabit per second connection. Fiber, when you run fiber between two devices, there are always two fibers. One's transmit, one's to receive. Obviously, transmit on one side, you'd want to connect to receive on the other side. This is usually used for enterprise networks from core router to core router. It may be used for fiber to the home. Used to be known as Fios. Verizon changed the name. It used to be Fios, stood for Fiber on Site, which I thought was kind of a cool sounding name. But now Fios, they say, stands for Fiber Optic Service. But anyway, this is getting more and more popular to have fiber to the home. And with MetroNet, they're trying to go through and do that in Lexington. Gives you a more reliable connection and a faster connection. Fiber optic cable design. If you click on each of these, we'll start with the core. The core is very precision drawn plastic or glass. Around that we have cladding, which is going to isolate the core to try to keep the light traveling straight down the line, and acts like a mirror and will reflect the signal if it happens to hit it. You then have a buffer, which is to kind of strengthen the fiber optic cable and cause the fiber optics not to break. You have more strengthening material that again is going to protect the whole cable. And then they say often they use Kevlar or something similar, like bulletproof vest, and then there's going to be an outer jacket. So this is kind of an in-on view, and this is a cross section. This kind of looks like it's a pipe. It is not. It is a solid cylinder. So don't let that image confuse you. There are different types of cabling. I usually ask my students, if you could buy a cable for the same price and you were told one bundle was single mode and the other was multi-mode, which would you get? And a lot of times the students say multi-mode because it means many or multiple. But I always tell my students everything's kind of backwards in fiber. Really, single mode fiber is better. What happens is it has a smaller glass core, so there's not as much room for reflection and bouncing around. And when you have single mode fiber, the core is going to be glass, and you're going to use a laser as the light source. In the case of multi-mode fiber, the core is bigger, and you can have multiple pass of lights, and if these arrive too much out of sync, that can cause for problems. Also, instead of using a laser, use a light emitting diode, an LED. This is good for a couple 100 meters. This one back here is several thousand meters. So, single mode is for long haul, and this is, like they say, on campus or in a business would be appropriate to use multi-mode. There are lots of different types of connectors. ST stands for straight tip. You have to make sure you get transmit and receive correct. These are subscriber carriers. They have a different connector at the end. LC stands for Lucent connector. Lucent is a vendor. And then these are duplex LC. These have a little thing around them. The nice thing about these is you cannot mess up transmit and receive. This will only snap in one direction, so you're sure to get transmit and receive correct. An optical time domain reflectometer. Sometimes I ask students to go out and research these and find out how expensive they are, but they are very expensive. You can find misalignment, which is where you spliced two pieces of cable and they weren't perfectly coaxial to each other. If you have a gap in the end of a splice or an end of a connector and there might be a bubble gap there, it can detect that. And it can also detect, you polish the ends of these before you join them together. It can also detect how well or not well that the end of the cable was polished. So these can do a lot of things to diagnose problems that you might have in your fiber optic cable. But like I said, these are not something you go out and spend $50 at Lowe's and get. This is a chart that compares UDP or copper cable with fiber optic cable. There's one thing that they always harp on in the Cisco curriculum is they'll give you a scenario that you're working in a factory that has lots of motors and you're doing the network. What type of network should you install? Well, the answer is fiber optic, because at least at frequencies that we live here on Earth with, not on the edge of a black hole, electromagnetic interference cannot alter light. So the answer would be you would want to use a fiber optic cable so there's no chance of electromagnetic interference. Notice that with fiber optic, if we need a higher speed, we're going to have to go to fiber optic cable. If we need a long distance, we're going to need to go with fiber optic cable. If we need to be immune from electromagnetic and radio frequency interference, we would need to go with fiber optic cable. Electrical hazards, I don't know exactly what they're talking about here, but I envision them if you accidentally touch an electric wire onto your data network cable, then where you would normally have a few volts DC, you now have 120 volts AC, and you may get shocked and injured, or you may damage your equipment. Electricity will not go over glass or plastic. Both of those are insulators, so you're safe from that. However, here's the disadvantages: higher connector cost, higher installation skills required, and safety precautions are higher. And what they mean there is, you can pull pretty well on a RJ45 cable and not break it. But if you pull too hard on a fiber optic cable, you could damage the core, either the glass or plastic that's in the middle. So they're saying you have to be much more careful when you're installing fiber optic cable. Also, you can twist a Ethernet cable a little bit and it'll be fine. But if you kind of twist or pinch a fiber optic cable, you may break the core in half. And then 4237, activity about some of the fiber optic technology we just learned about. You can go through and check whether this is multi-mode or single mode, and then check your answer at the bottom. So you can do that on your own. And this is the point that I wanted to get to in Chapter 4.